嗯，要想做，想做啊，就看你资料。这个就讲资料什么？资料就讲，因为它的 partial series 是没有 convergent，那么它的就是当 m 所以 infinity 的时候就是 convergent。那另外一个讲它不是 absolutely convergent 那个我们之后才会懂的。我觉得第一个够用。那个图片，那个是 definition of 那个，如果它现在没有 convergent 的话，这样子它这个 infinity 就不会，它的 sum 就会 converge，就是那个infinite sum 是那个 partial sum 的意思。就我只要写一个解，写下来就可以了。如果解有好就写它，因为 partial 没有。那你就要写为什么 partial 没有，然后它的 partial sum 是什么？还有一个对1.3，1.3，嗯，我是不是要用到那个就 integrate test 来做？你可以呀、你这个可以。我要先讲它是，我先讲它是 continuous positive 无尽线。difference。对呀。你的题目是我选的还是你自己做的？是你选的吧，是我选的。啊，我像是吧，我可能有些看错。感觉你有啥来问我1.3，我觉得这个好像多了，对不对？做过我忘记调这个礼拜了。可能多了一些，来一些。你先做前面直接。你 try 看。它是在 under 什么 under racial test，integrate test，这一个 section。对，section 就是也是应该这样就 try integrate test。感觉又要用那种的东西吧，那你才可以把那个 non-excited 哎，你可以吗？对你才可以把 non-excited 应该是吧？Power series 跟 P series 是一样的。对呀，对呀，Power series 是另外一种，慢一点会介绍。今天会介绍吗？不知道。呀。是吧？我可以这样子做。I mean 它这是 n over one over n 然后 square root。我就这样写，然后写到这边的时候，我就写不下去啊，因为我不知道要怎样把这个 x 写下来，我就把它变成小数点，就把这个乘法2变成小数点。这个不是 P series 吗？你要用 integrate test 也可以啦吧？这是1.3，但是你也不用变小数点，因为这是11.3哦。对我讲，你什么小数？什么意思叫小数点？就是你要 make sure 不用小数点啊，其实你小数点都没有关系的，因为它就是1 over 1.2，就这样吧。它是一个号码，你不是只要知道它 convert 不 convert 就好了吗？你不用知道它是什么东西嘛，对不对？而且这个好像是 P series。
square root 2就是大过1。
Yes，
都可以哦，所以很多方法。Why you move back again? Huh? Undo. Huh? Control Z. Undo. Can someone help close the door? You. Okay. Good afternoon to everyone. Why is it so few people today? Where's the rest? Huh? Oh no. Die. So bad on you. So bad. How many of you come from UEC background? Most of you. Okay. Are you guys easy with English or no? So far okay. Some of you okay. How should I say? Yeah, kind of important for language because most of the student lost because of language. I mean, lost in the lecture. So maybe I'll try say some important stuff in Mandarin so that you can catch it if it is really really important. Okay, but otherwise, I mean, I will say in bilingual. So if I speak in Mandarin, I'll speak in English at the same time. Okay, so there's so that there's no message lost in translation. Okay. Okay. Yeah. But those in mathematics terms, right, will always be in English. Okay, because I never learned Chinese one before, so I cannot say anything much. Okay. So knowledge isn't free. You have to pay attention. Okay, please pay attention. There's a math help center. Okay, if you want to get some help for your assignment, you can go to this. I think it's run by a PhD or master student. Okay, you can get help. And from 1 to 2, Tuesday to Thursday, A5G08, if you want to drop by. Okay, you can get help for your assignment here. Okay. Yeah, I think it's posted in the Teams math group as well, if you notice. You all are in the maths team, right? Yeah. Oh, it's there as well. PhD students or master students. Yeah. Teacher also got. Teacher also got. You know when is it? You know when is it? Don't know. I thought I put my office hour on already. Yeah. This one no. This one is the PhD and master student. Yeah. Okay. When's your assignment due again? 11. Next week. Okay. So please do it as early as possible. Don't wait until last week. Okay. Yeah. Any question from last week? Have you tried all the homework yet? Not yet. Please try. I already posted the solution also. Okay. Yeah. Please try, and then if you have problem, you need to ask here. Okay. So I'm not sure how you learn mathematics before. Okay. Maybe you just learn by imitating the example. 就是说，你看一个例题，然后你尝试的重复的做，OK，看到换不一样的号码，OK，by just changing number. But university level mathematics, you have to know what is going on. OK，你需要明白这题为什么这样做，OK，为什么用这个方法。So you need to ask why we use this method, why this method work. Does other method work as well or not? Okay, which one is faster? Which one is easier? Okay, you should ask yourself. Okay, don't be contented by just solving the question. Okay, 不要以为你就可以 solve 那个 question. Okay, 很简单的 solve. Okay, this is not how a university level maths work. Okay, so you need to definitely understand why. Okay, so that's why I ask you to ask questions more. Okay, ask question more in class. Okay, yeah, and then how should I say? Don't just accept everything I say, okay? You should question more, okay? Okay. I realize I'm not sure it's of course because of Asian background. The students tends to how to say. Okay, last time I talked about spoon feed, right? So it's like not just spoon feed, it's like you want to try and follow some rules. I was like that before as well, okay? 所以我以前也是这样，就是想找一些规则来跟。但是，but when you go into a research world or a world of unknown, okay, there's no rule for you to follow anymore. This is what I realized when I start doing research. Okay，当你走进一个未知的世界的时候，已经没有规则给你跟从了，你就是那个创造规则的人，你就是把那条路走出来的人。Okay, so don't be obsessed with some just method. Okay, don't be obsessed with method. Okay, you need to find a way to solve problem. Okay, so I encourage you to solve in different way. Okay, I don't say that this question need to solve in this way, that question solve in this way. No. Okay, you can do any way you like, and then make sure that you can do it efficiently. That's all. Okay. 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 We will talk more about these things again. So let's continue. Okay. So if you don't have question, I will assume you already okay with the content. So be aware. Okay, so make sure you ask question if you get stuck. Okay, let's continue. So last time we what have we talked about? Maybe recall a little bit what we did last time. Yeah, let's recall. So what did we do? Okay, we talk about, okay, let's recall the stuff on the series, right? Sequence a bit old already, so let's talk about series. So what kind of series we have met before? We have met P series. Okay, anyone still remember what's the P series looks like? Sum of what? Sum of what term? Where n to the power P, where n going from 1 to infinity. Okay, so when does this converge? When does this converge? If P is greater than 1. Okay, and diverge when P is less than equal to 1. So what kind of example you should keep in mind here? One very classical example. Very classical example. Yeah, when P equals 1, what is that? It is a harmonic series. Yeah, harmonic series. 1 plus half plus 1/3 plus. It's a harmonic series. Harmonic series diverge or converge? And then this is the counter example for what? Test the converse of divergent test. Okay, so this is a counter example for the following statement. So what's the statement? If what? Yes. And okay, so this is a counter example. Why? Because the an converge to 0 as 1 over n go to 0 when n get large, but the sum diverge. Okay, so this is a counter example for this statement here. Very important. Okay, so let's continue. What kind of we have? We have geometric series, right? We have proved this from the start. So how does geometric series looks like? Hang Wei, how does a geometric series look like? How about a ratio, something with ratio? Another Hang Wei. Divide, multiply, okay. From 1, n equals to 1 to infinity. So R is the common ratio of your geometry sequence, right? So R, okay, where is the common ratio of the geometric sequence. So what is geometric series? Series is a sum. Sequence is a list of number. So you add the sequence up. So become geometric series. Okay, so when does this converge? When does this converge? Seng. Hey, I asking you, don't ask others. In exam, you can cheat, man. Yeah. So now is the time to test you. So when does it converge? Don't tell her. You are not helping her, okay? Yeah. Less than what? Can see or not? One is less than R. One is less than R, like this. So, huh? Say Chinese also can. I don't know. Okay. You don't want to guess. Or this is your guess. Okay. Right. So usually right, something wrong with not totally wrong, but we won't write like this. Okay. Something I want to tell you about this mathematical writing here. Okay. Normally, when we talk about unknown, right, we will say it first. Okay, instead of saying 1 less than R, we will say R greater than 1. Okay. But is it true that it converge when R greater than 1? No. Okay, so when does it true? As the value of R is less than 1. Converges if absolute value of R is greater or equal to 1. You see? Okay, so I mean, wait, for formula, right? Okay, you cannot just memorize, 不要只背那个公式 ，right? You need to make sense of it. 你要理解哈，这些公式是活的。What do I mean by 活的？Okay, you see, R is greater than 1. R is greater than 1. What does it mean? For example, take 2. If your R there keep squaring by 2, do you think that the number will get larger and larger? Comparing to a R that's less than 1. Think about it. Think about it. Okay. Yeah. Okay. 所以想一下 okay, must make sense of the formula. Okay, otherwise the formulas will just look very cold. Yeah. Think about it and make sense of it. Can see or not from the back? If cannot see, I turn off the light. Red cannot see. Other color then okay. Okay. Then yellow color can. How about this color? Okay. White can. Okay. Let me see which one is that one. Orange and what? No, not good. Purple, not good. Okay, only 3 color can use them if I don't turn off the light. Okay, we'll see how. Blue, okay. Blue, yellow, white. Blue, yellow, white. Green. Okay, okay. We'll use this 3. Okay. Yeah, okay. So geometry series, P series. And then what else we have learned? We have learned the direct comparison test. Okay. So what are we comparing here? What are we comparing here? How are we comparing here? How are we comparing here? Let me see. Seng, what are we comparing here? Yeah, okay. So first we compare what? What are we comparing to determine whether the series conversion? Huh? Can you just say? Series is what? Yeah, okay. More specific a bit. 交通 here. 交通, yeah. What's the condition on the direct comparison test? Yeah. Can you understand my question or not? What's the condition you need when you apply direct comparison test? Can you understand? You know the answer? Don't know. 中医. Yeah. Okay, so you are comparing two series, okay, the term inside the two series. So suppose that AN is greater or equal to BN and less than or equal to BN for all N, okay? So where are these AN, BN from? So you use them to form a series. You use them to form a series. And then what's this part for? Seng, do you know? Why all of them have to be greater or equal to 0? Tell me. Why? What does greater or equal to 0 mean? Say anything you like want to say. Okay. Okay. I haven't asked you this question yet, but you filled it in, never mind. Okay. No, my question is why? Why we want AN greater or equal to 0? Hey, please don't translate my word, okay? Because I need to talk to her. You cannot be her translator forever. You have to follow her forever. If she don't understand, she should ask me. Okay? You understand what I'm asking? Why AN have to be greater or equal to 0? 为什么 AN 要大于等于0？ Why? Or tell me what does it mean by AN greater or equal to 0? 什么意思 ？AN 大于等于0是什么意思 ？Decreasing? No, no, not non-decreasing. No. What is non-decreasing? What is non-decreasing? Huh? What's the property of non-increasing? Who is non-decreasing or non-increasing? What's the object? Not series. Huh? What do you mean? What do you mean by related to the R? What R? Ratio R? What kind of R? No. No. What's this non-increasing decreasing for? For sequence or series? It's a sequence, right? Okay, so this is a sequence. when does the sequence non-decreasing? If what? You remember the picture, so how to say it mathematically? When? Yeah, say an less than an plus 1 for all n, correct? Okay, so non-decreasing is for a sequence. Okay, so now you're a bit confused, is it? Why I put an here? Why I put an here? Are you confused? You're confused, right? Okay, so if you're confused, you should ask. So there are two things here. So sometimes I'll write this as an. This an is also the same as this an. Okay. So here an here, what is this? This is just a number, a non-negative number. Okay, so this is a number, but but the bottom one is a sequence. Okay, so you need to be careful when I say an is a sequence or number. Okay, so yeah, I also encountered this problem in my other class. So when you see this symbol, right, you see a lot of symbol. I will use a lot of symbol, A, B, C, D, phi, gamma, everything. But the most important thing is not the symbol, it's what the symbol represent. OK， 不是那个符号是那个符号代表的东西。I can change the name. For example, Han Wei, you can call Han Wei Han Wei. You can call Han Wei Ethan. You can call Han Wei what else? What else people call you? Maybe your family or your friend. Okay, genius. Okay, he like genius. Okay, so but no matter what name you call, it's still that person, Okay. So very important when I talk about a number or a symbol, what's the thing behind the symbol is very important. Okay, if you are unsure, you should ask. Is this a sequence, or is this a number, or is this a set, or is this a function? Okay, so in mathematics, there are typically two things: set, function. Okay, set and function mostly. Okay, so sequence is a set, and then an is an element of the set. Okay, so be careful. Especially these notation stuff, I need to be careful. If you are unsure, please ask. Okay. All right. So good. So just now I have if I have a comparison between an and bn, where bn is greater or equal to an greater or equal to 0. Okay, Seng tells us that the sum of bn is convergent. Then, if the sum of bn is convergent, then the infinite sum of an also converge. Did I tell you how to think about this statement last time? Still remember? Forgot. 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 Anyone remember? Yeah. So less than or equal to alpha bigger than. Yes. Okay. So how should we think of this? So like what I said before, I like geometry stuff. So you can think of an like this. Okay. Maybe not have a growing pattern, but you know that bn is always greater than it. Okay. But when you add them up, add the blue bn up, you know that it is finite. Okay. You know that it is finite. But like, what's your name again? I forgot, sorry. Yeah. Edward. Ivan. Okay, right. Ivan. Okay. Ivan. So when the sum of bn converge to a finite sum, okay, an is always positive. Okay. So it must converge to something in between the sum of bn and 0. Okay. So this is the key part of this zero, you know. If this AN can grow to negative, can you imagine what happened? You can go forever negative as you like. Then it doesn't converge again. Okay. So the bound of the zero and the infinite sum is very important. Okay, of Bn. Question? Any question? Okay, if we don't have this condition here, we might get divergent sum of AN because you can make AN as negative as you like. Okay, does it make sense? Some of you confused. Any question? Ask question. If you want me to repeat, also can. Okay, if you ask some stupid question, also can. Okay, this is time for you to ask. Seng, okay or not? Okay. Okay. So and then the contrapositive of this statement is if AN infinite sum of AN diverges, then the infinite sum of BN also diverge. Okay. Good. Okay, so this is what we did last time. Please make sure to exercise how to apply these tests. Okay, we will learn more tests. Hopefully, we will go into a power series today. Okay. Okay, so next new. So this is a new stuff. Let's start with a new stuff. We start with limit. Okay. So you see, once you see this word, right? What should you think? What am I comparing now? Limit. Okay. So you need to think about. I need to compare limit now. Okay. So what kind of limit I want to compare? Okay. So I will tell you now. So first, suppose that AN is greater or equal to 0, but BN is strictly greater than 0. Okay. And then the limit I'm computing is AN over BN. Okay. Then let it be sum F. Okay. So can you see from here why BN have to be strictly greater than 0? Why? Because you divide by BN. Okay. So AN divided by BN. Okay. So you cannot divide by something 0. Okay. Huh? Okay. So you have these two conditions here. So how to tell the sum of AN or BN converge? So there are two cases. So when L is finite, okay, not 0, finite, then the sum of AN and sum of BN diverge together. Okay. Do you know what does this mean? So if you happen to know one of them converge, okay, you compute the limit in some finite number, then the other also converge. If one of them diverge, the other also diverge. Okay. So now you need to train yourself. When you see this kind of statement, right? You need to think about how to use it. Okay, think about how to use it. Later I'll show you how to use it. Second case is if L is 0 and Bn converges, then An also converges. So try and think about it. So when does L can go to 0? When is L 0? When is L 0? When Bn is very large. Okay. So it says here that if Bn is very big, okay, but Bn also converge. Bn is already very big, but still converge. Okay. So AN comparatively small should converge as well. Okay, so this is the idea there. Okay, how about the first one? What does it mean by the ratio equals to some limit? How is the growth? How is the growth? So the growth is equal to a constant. Okay, so if one of them converge, the other converge. One of them diverge, the other diverge. Okay, because they grow in a linear way. Okay, grow in a linear way. Okay, is it linear? I think it's a constant, just a constant. Okay. Okay. So let's see how to prove this. Right. So let's see how to prove this. Blue, okay. Okay. So let's see how to prove this. Okay. So this proof uses direct comparison test. So let M be let small n and the big M be the bound of this L. Okay. So because L, so let's look at the first case, right? So let's look at first case. So suppose L is finite. Okay. Then we can find some M, small n and big M. Okay. We can find some small n and big M. Okay. So what does this give? So then n large enough, we will get the inequality an over bn is greater than m and less than bn. Does everyone know this or not? Why is this true? This one is from calculus 1. So this is the definition of limit of an over bn. So when it is very close to L, I can make the term very close to L, such that the inequality holds. But if we want to write this precisely, we need to use epsilon delta. Okay. If you like, you can do it. Try and write it up, work it out. Okay, and then you can present it in your project. Okay. So let me comment something here. So to do this precisely. Epsilon delta. Yeah, epsilon n definition. Okay, but to see why is this intuitively true, because when the limit is equal to L, okay, remember what I said last time, the tail of the sequence will evolve around L, very close, arbitrarily close. Okay, so when it is arbitrarily close, you can make some gap between L. Can you imagine what I say? Let me draw to you what I say. Okay, so this is L. Okay, your tail is growing arbitrarily close. Okay, then you can find some epsilon here. Okay, so maybe this is your M, this is your Bn. Like this. Okay, make sense? Okay, yeah. All right. So what are we getting here? So next we want to show whether they converge together or diverge together, right? Okay, so we're gonna use direct comparison test. Okay, so from this inequality here, we get m times bn less than an less than b times bn. So from here, what can you do? From here, can you deduce anything or not? I have comparison between sequence. Can you do anything to it? Do I know anything about sum of Bn, sum of An, and sum of Mbn or not? Do I know anything about them? Jingzhen. Sorry? B. Why is Bn is convergent? Why is Bn convergent? Our condition. No, there's no condition here. No condition of sum of Bn. Any idea? Can you tell anything about sum of Bn and An? Genius? You can't tell. Contradict the. It's okay. I mean, what's the comparison test statement again? How to use comparison test? Recall. I just recall half an hour ago. What's the statement? Comparison test says direct comparison test. What's the statement? Ratio of L? No, that one is the limit comparison test. I mean direct. Yeah, direct comparison test. Suppose what? Recall again. Today we recall twice already. Yeah, suppose sum of Bn converge. If Bn converge, then sum of An converge. But what's the condition on An and Bn? Okay, so 0 less than equal to An, equal to Bn. Okay. Okay. So do we have this condition or not? For all N, be careful with this quantifier here. So do we have this case or not? Do you have this condition? Yes, sir. How and where is it? Show me. Is anything here greater or equal to 0 or not? Anything here greater or equal to 0? What's the condition on An and Bn? An is greater or equal to 0. Bn is greater than 0. Okay, so do we have them greater than 0? Of course, this is greater than 0. How about Mbn and capital Mbn? What are these M and Bn? Where are they? They are they are what? How do we pick this M small n and Bn? Okay, yeah, and then Bm is greater than M. Okay, so in other words, okay, we just pick them from the real positive. Okay, real positive. Okay, so positive number multiply positive number, you still get positive. Okay, So everything here is greater or equal to 0. Okay. Okay. So how do we apply this direct comparison test here? If what? If sum of MBN, the capital MBN converges, then sum of AN also converges. Okay. And then anything else? Anything else? Is this the statement we want to get or not? Is this the statement we want to get? What's the statement we want to get? Let's recall. Sigma AN and sigma BN converge. Okay. But here got capital MBN or how? How to turn the infinite sum MBN to BN? And take the M out. Okay. Take to where? And then? Okay. So more precisely, so if Bn converges, then M times sum of Bn also converge. Right, remember? So we can multiply constant to a convergence sequence and then still converge. Okay. Okay. So if we have Bn converges, sum of Bn converges, then sum of Mbn also converges. And then by direct comparison test, okay, sum of An also converge. Okay. So the idea maybe you should put like this. Okay, so they converge together. Converge together, I think there's another direction you need to prove. So you need to prove that if sum of AN converges, then sum of BN also converges. Okay, but how to prove this? Yeah, so we can go about the small MBN. So if sum of AN converges, then what? Then the sum of small bn, mbn converges. Okay. And then how we deduce to bn? We just divide by 1 over n. Divide by n, which is multiplied by 1 over n. Okay. But sum of bn is equals to 1 over n sum of bn. Okay, so it converges. Any question? Any question? No? Okay. Okay. Yeah, so similarly you can prove it for divergence. Okay. So for the part of diverge together, we will left as an exercise. Okay, you can try similar argument. Okay. How about prove the last statement and then we will go into example. So the last statement is I want to show if the limit is 0 and the sum of bn converges, then sum of an also converge. Okay. So suppose what? Suppose the limit is equals to 0. Limit of what? An over bn equals 0. Okay. So this means what? This means just now we said already, Bn is getting bigger and bigger and bigger. Okay, in particular, An over Bn is less than 1. Okay, for large. Okay, you can make it as small as you like, right? 0.01, 0.0001, 0.000001. Okay, but we choose 1 is enough. Okay, because we want to use some comparison tests. Okay, why is this useful here? Because An over Bn less than 1 implies An less than Bn. Okay, so are we happy if you see this? You can compare An and Bn already. A and Bn both positive. Okay, greater than 0, non-negative. So we can, what can we do here? What can we do here, Ivan? What can we do here? Huh? Once you can compare the terms, what conclusion you can draw? Yes. So what test you use? Yeah. Mm-hmm. What do you use? Again, same trick. No, we are proving limit comparison test. Direct. Okay, so the direct comparison test tells you what? Tells you if Bn converges, then sum of An converges. Okay, which is what we want to prove. Okay, so if sum of Bn converges, then An converges. So by comparison test, since sum of Bn converges, sum of An also converge. Okay. Okay, so let's look at example, right? So let's look at example. Okay, what's the example here? So the example here we want to look at is 3n over 2 over n cubed minus 2n squared plus 11. Okay. Yeah, so if we're gonna use limit comparison tests, what a, n, and bn you want to consider? What kind of an and bn you want to consider? Sorry? Yeah. Yeah, try. But what? Wait, say again, say louder. I cannot hear. Uh-huh. Yeah. And then what an you want to pick? Correct? Yes, correct. And then bn is sure. And then yeah, continue. Finish your sentence. And then like this. Like this. Okay. So what does the statement say? If you do this, what does limit comparison test give you? You are finding the sum of 3n minus 2 and the sum of n cubed minus 2n squared plus 11. Is this what you want? Is this what you want? Is the sum, is this two sum is what you want? No. Huh? Is this the same sum you started with? Yes or no? Huh? Yes. Yes. Huh? Yes. Let me write to you. So, what do you mean by this is the same? Are you saying these two things are equal? Huh? No, right? Everyone agree not the same, I no need to show, okay? So they are not the same. So seems like you pick the wrong AN and BN. Okay, you want to know about the sequence 3n over 2 over n cubed minus 2n squared plus 11. Right? So this means what? One of them have to be the whole fraction here. Correct? Get it or not? 中意啊? You don't get it? Don't understand? Okay, so go back to your answer, right? You define A and Bn as this two. Correct or not? Okay? But what does limit comparison test give you? It tells you the sum of An and sum of Bn. Correct or not? But is sum of Bn or sum of An is the sum that we are hoping for? 是我们希望的吗? No, right? Okay. So how to get this sum here? Make for what? Say this, continue, finish. Separate and then? Yeah, I write it out. Okay, let me follow you, okay? So now it's a tutorial time. So 3n minus 3 plus 1, and then like this.
Yeah, and separate the one, please.
Like this, like this. And then, for what?
Oh, making no sense.
Okay, I like your wild thinking. Okay. Okay. Sure. Okay. So follow my logic here, right? So if I define AN or BN, okay, I'm looking at the sum of AN or BN, but I'm looking for the sum of this thing here, 3n minus 2 over n cubed minus 2n squared plus 11. Okay. So this means that I need to make one of them be this fraction here. Correct or not? So that the sum of this fraction will appear in my theorem later. Make sense or not? Huh? Does that make sense? Something like this. So if I make AN here, okay, then we will have some statement about my sum of AN. Right? Sorry? This is your choice now. You need to find a choice BN. Okay? So we need to think of a way how to use this theorem here. Okay? We need to think of a way how to use this theorem here. Okay? I already have AN. I have AN already. Okay? I have AN here. Okay? So what result you want to get? You need a help of Bn. Okay? So if you can find a Bn, such that when you take the what? Take what? Take what? Division, divide. Quotient, yes, that quotient, correct. So when you take a quotient, okay, when you take the quotient of Bn, you get some limit, okay? And then this limit will tell you when does they converge or diverge, okay? If this limit is finite, okay, then you know about Bn. If Bn converge, then An converge. If Bn diverge, An also diverge, okay? But when L is equal to 0, okay, and you know that Bn converge, then the sum of An converge. Okay. So now you need to make a choice now. Okay. Okay. Your life is about making choice. So what choice you're gonna make? What BM you're gonna take? Okay. Remember, you want to take a quotient. Can you pick a choice such that when you do the quotient, you will get easier computation now? What kind of BN you want to take? Huh? Who say one? Take one. One. Take one. Okay, I take one. So I take one. Let's do experiment. Okay, and we take one. So sum of one. Sum of one is what? No. Sum of one is what? No, infinite sum of one. Yeah. Diverge, right? Diverge. Okay, so diverge. So you see, if you pick your Bn diverge, what happened? Huh? You should hope for your An to diverge. And then you should hope that the limit here is a finite number. Otherwise, you know nothing. Because the second condition here doesn't work already because your Bn diverge. Okay, so this is the only case you need to hope for. L must be finite and then An diverge. Okay, so let's try. Yeah, let's try. So let's compute limit of An over Bn, which is just An, right? Okay, so what happened? How to take this limit? Divide. Okay, good. So divide by n cubed, so we get n squared minus 2 over n. 1 minus 2 over n plus 1 over n cubed. Okay, so what's this? This is 0. Can you say anything or not? If L is 0, Bn have to converge, but your Bn diverge. So you cannot say anything. Okay, so this choice is not good. Try another choice. 3n over n cubed. Okay, let's try 3n over n cubed first. So let's do second choice. Let's call it Cn. Okay, 3 over n cubed, correct? Square or cube? Square. Square. Okay. So let's compute. What is An over 3 over n squared? Okay, so what do you get here? What do you get? So you get, yeah, let me think. 3n squared over 2n cubed. 3n cubed of minus 2n squared over 3. Should I multiply? Just multiplying first. Correct? Correct? Okay, so how to compute this limit here? So divide by n cubed again. Right. So over 3 over 6 over n plus. And then equals to 1. Okay. So L is in between 0 and infinity. Okay. So do we know anything about this or not? 3 over n squared. Converge or diverge? Okay. So sum of 3 over n squared converge. Anyone know why? Two. Yeah. Converge due to P series. When P equals to 2. Okay. So 1 over n squared converges, and then constant time a convergent series also converge. Okay. If you like, also with property of convergent series. Okay, so what am I writing here is sum of 1 over n squared converges. So 3 times 1 over n squared also converges. Okay, so this is what I mean by the reason here. Okay. Okay, so they converge together. So we can use the limit comparison test. Okay, so we can use the limit comparison test. If L is 1, okay, L is in between 0 and infinity, then they converge together. Okay, we know that sum of B. So how do you know, like, how do you think of this example here?
The numerator and denominator. Highest power.
Okay, you take the term with the highest power. Is it?
That's all.
Uh-huh. Yes, yes, yes. Does everyone get what he said? Everyone get what he said? Take the highest degree term, okay? But not just this will work, right? I can also just take 1 over n squared. 1 over n squared also work. Okay, where I think I will get 3 instead of 1 for the limit. But 3 is still finite. Still apply. Okay, so there's only not just one answer, but that's the logic way to find the answer. Okay? Okay, can or not? Actually, this is really similar to how we compute the limit here, where we divide by the highest degree. Okay, but now you are dividing an. Okay. Just now, you only can play with an, but now you can play with bn. Okay. Yeah. Okay. Good. Let's see. How about we do one more example and then we take a break. Okay. Let's do one more example and then we take a break. So I give you 3 minutes and then try and check the conversion of this this example here. Okay. Try and check the conversion of this example. I give you 3 minutes. You can discuss now. You can talk as much as you like now. Yeah. Use the logic just now. Okay. Similar logic. Okay, idea? Any idea? What AN should we take? Which one? 1 over square root n squared plus 19. Okay, you want to use the original sequence from the series. Then how about Bn? 1 over n. Okay, let's check 1 over n. So how about we determine what happened to 1 over n first? What's the what is this divergent or convergent? This is what? What series is this? Yes, this is a harmonic series. Okay, it's a harmonic series. Okay, so it diverges. Okay, so now what cases you want to hope for? You want to hope for the limit to be finite or zero? Finite. Okay, so that they both diverge. Okay, so let's see what's the limit here. 1 over square root n squared plus 19 over 1 over n. And then this is just what? This is just n over square root n squared plus 19. Okay. And then how to compute this limit here? How to compute the limit? Just divide by n on top and bottom. Okay. Then altogether you will get 1 over square root 1 plus 19 over n squared, which in this case your limit is just 1, okay, which is finite. Okay. So by limit comparison test, yes, the sum here diverge. Okay. Okay. Any question? Okay, I understand. Know how to use limit comparison test. Any question before I take a break? Tony or Ivan? Okay. Okay. So the last example we will left as homework. If you have problem understanding, then we can discuss again. Log n over n squared. Okay, try and see if you can prove whether this converge or not. Okay, left as a homework. I will provide solution. Okay, so let's take a break until 422. Yeah, we come back at 422.
comparison
嗯哼
test 啊
嗯哼
那你讲的是那个 AM 会小于0，然后你把我这样的图，因为等下我就 pause for question 啊，这次，
哦
这是
OK，
AM，然后这是
嗯哼
颜色随便就可以。
，OK，然后
然后当 AM 它小于0的时候，AM
哦
小于 0，
OK，A 小于0啊哈，
这样子我是不是可以讲是我可以选一个 BN，然后它是负的，然后但是它 convergent，然后我 AN 就会 convergent，它也是负的，就像这样子
哦，你是说这个 statement 啊？啊，对，
可以啊。
可以，你可以 prove，
那直接这个如果是一个
可以 prove，
也是可以
从我那边就可以推出来，
从哪一个
从刚才那一个，从刚才那一个，从 direct comparison test 就可以推出这句话。不要试下 proof，讲 proof 没有，先理解先，知道可以，我就跟你说，他可以从那边 proof 出来
yes
啊，
从那个 direct
从那个 direct comparison test 就可以把你这句话 proof 出来。
有
因为像你讲嘛，在图上面它只是把上面的东西这样整个仿下来嘛，对不对？所以仿下来在数学上面讲解释这个东西
projection
project
硬是啊
OK 啦，是 project 啊，不是 project 就是 reflect，
reflect
就是反射。 因为它是镜子嘛，镜子反射过来嘛。
哦，这样，
呀，所以
嗯，
我讲它可以从那边推出来怎样推？你要不要想一想？
用 quantifier 是不是？
没有，quantifier 不一变，
对比
不一变，
对比是什么？
就是你有那句话，怎样推出这句话？就是刚才那句话有 if 这个 then 它 converge 嘛，所以你现在有 if 这个为什么 converge？
它是一定恐怖什么的，可以擦掉的。嗯
哎，你的 if 跟那你的 if OK OK OK，你可以这样理解，可以呀，可以，对，可以，
我有不起，那些给人过。那你讲出
啊，
真的是讲用哪一句话？你是讲用那个打的滚水鱼的？
就是用这句话，这句话 direct comparison test 用这句话，因为它这个是正的嘛，你那个是反的嘛，对不对？
Yes，
所以用这句话可以推出你这句话。
这句方面
你要不要想一下？你想出来可以加进你的 project 里
有
啊，没有很难，但是哼，
我们就是 我们的 quantifier 是 P plus Q，对不对？如果
对
过来的话就是
没有反过来，你这个不是在反这个东西，你这个只是反它的条件罢了。你是 P，你的是不是这个跟这个没有关系。你这个如果你要做这个东西的话，
对哦，不是没有关系，
不是这个东西。
结果不是 condition。
对，你是把它的那个你只是把它 condition 都换掉了。
哦，condition 变成 conclusion 了。
也不是这样讲，不是这样讲，这个是不是这个是全新的 statement，这是全新的 statement 那
全新 statement 我用这个来 prove。
可以有关系的这两个，
哦
这两个有关系的。
哦，对，还有我还要问你，
你 try prove 啊，如果不能 prove，你在拜三拜四再问哦。
那老师你有没有什么比较资料啊？但是可以读吗？
什么
I mean，
读什么？
如果我要做 project，我要写 reference 啊。
你就谷歌一个 topic，然后谷歌 topic 它会给很多东西嘛，你就按进去看咯。你按进去看了过后，它可能里面又给 reference，你就去那些 reference。
哎，如果没有给 reference，他直接给你一些 proof 啊。我如果想要找到 proof，他直接 reset 了，他直接给你 proof 了，他没有 reference。
应该等一下我想一下，你要做模型，你先跟我讲你要做模型，
因为如果我要 proof 的话
你要 prove 什么？
比如讲我要 proof properties 啊，
什么 prove？
就是那个
那个
EV law，
书本应该有啊，
日本有没？
有应该是有 textbook 有啊，textbook 有的，textbook 就有，那个 textbook 就有。
但我只有这一个 reference 嘛，这样我自己
正经啊 reference 不多啊，我不只 reference 我只是要 keep track 你从哪里来的就，我没有让你
我还是
写一大堆。
比较感兴趣这个，
啊，你不要感兴趣呀，写这个我也觉得蛮有趣，因为
感觉很难。
呀，如果你不写的话，可能要出在考试。
哦，行哦，
OK，没有了，写一下你想不出的话，拜四再说。呀，我觉得这个蛮不错啊，但是可能不够长啊，可能你还要再做其他东西啊。
我就这样，我不那个晚点。
你可以做其他呀，因为我这个应该是不够长。
这样子如果要做 ASDB notes 里面的
也可以啊，也可以啊，呀也可以，只要你做课以外的东西的，就是说不是讲，就是课上过东西，但是我们没有去钻研它，或者我没有来不给你看，你把它清楚的写出来，就可以写在那个，就算课本有也不用紧，但是你要明白啊。
还有一个，因为那个 direct comparison，它不就是下载吗？什么意思？就是这个，就是一个 sequence 里面，它就是 for all m，对不对？然后它
好，什么情况？
就是一个，I mean，它就是一个 set 就不是 sequence 来吗？
就说它是一个 set，我听不懂。他们全部都是号码来的
我
，AN 是号码，BN 是号码。
I mean，它对于所有都成立了，对于所有。
好啊，没有问题啊。然后跟 set 什么关系？
这样我不可以写成这样子咩？
什么叫做 set 大过一个 set 呢？我们
它里面的 element
没有人这样讲啊，
没有人讲。
没有这样的 definition 啊。你不能够随便比较两个 set 啊。你能够拿水果来比蔬菜吗？
也是哦，
啊，
也是。
对啊，没有人 define set 大
就是要
过。
它就是要 define 的是，我们只能 define 的是它里面的 element 啊。
因为里面的 element 是号码来嘛，号码有分大小，可以吗？
如果我要比较两个 set 的大小，哦对，
比如现在两个 set 的大小要 take 那个 cardinality 啊。啊？什么可以什么？啊，不可以，不可以。我讲不可以，就你要 reference 那个 website，它肯定也是从某个地方来的，去找回那个最原始的那个。什么？什么？
是说一下那个 template 有没有？
我觉得 template 啊，有啊，我放在，这没有什么 template 啦，其实我有放一些 latex 的 template 罢了。你应该有更好的 template 吧？我觉得，就是我没有 template，只是说教之前我一点那个 cover 可以这样，也没有什么 template，就跟着我的 format 就行了，跟着我的 format。如果你硬要说 template format 的话，你可以去看一下前一年的人们，前一年人怎么做啊，就这样就行了，没有什么特别啊。好像放在 week 10，我放在 course info 里面。对，yeah， 差不多时间我会教你们教那些 drop 之类的。Okay, are you ready? 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 Let's take attendance first. 光业 ，OK。有缘 not here。卓金，金生，陈江，Ivan，知莹，Larry，罗浩，钟毅，小彤，邓康，一心，罗善。Was your leg got problem last time? Your leg, huh? Is it you? Not you. Whose leg got problem? Are you okay now? Okay, okay. 托汉伟 ，Sydney，燕如，若兰，汉伟。Okay, yeah. Have you tried this or you haven't tried? We go first. Keep going, huh? Haven't tried, okay. Yeah, let's keep going. So next, we'll talk about alternating sum. Okay, let's talk about alternating sum. So What is an alternating sum? Oh. So sometimes, right? Hello? Yeah. So sometimes, right, when you take a series, it diverges, okay, because it grows larger and larger and larger. But what if you add the first term minus the second term, add the third term minus the fourth term, and then do it alternatingly? Okay, does it still converge? Okay. Yeah, might converge. So what's the condition here? So an alternating series is a series of the form B1 minus B2 plus B3 plus B4 and so on, where Bn greater than 0. Hey, what happened to Qiao Tong? If you need to call, maybe you can go out and call. Huh? Okay, so this is an alternating series, and then we have an alternating test, okay, alternating series test. So when does it converge? Okay, like Zheng Kan say, right? Zheng Kan. Okay, so it might converge. So when does it converge? Okay, so if the alternating series satisfy two conditions, so two conditions here. So what's the first condition you should satisfy? So the first condition is you should always hope for Bn to decrease. Yeah, right. You want the An to get smaller and smaller. Okay, but in this case here we call it Bn. So to reduce confusion, let's name our series first. Okay, let's give a name. So let's give our series a name. What should our series call? Let's give this a BI name. Okay. So let's call our B series here BI. Okay. And then you need a alternating series. Okay, how to put alternating series here? So there's a sign depending on your n. Here is I. Equals to until n. Or infinity. Okay, because it's series. Okay. Cannot. Doesn't work, I think. So because the first term here is a positive, okay, but the first term here is negative. So how to make it positive? I plus 1. Okay, I plus 1 also work. I plus 1 or I minus 1. Okay, you shift right or left. So first condition you want to satisfy is Bn is greater or equal to Bn plus 1 for all n. So meaning n plus 1 smaller, getting smaller, smaller and smaller or equal. Okay. And then second condition you need to satisfy is it not only getting smaller, it has to get smaller as fast as possible. Okay. Need to go to 0. Okay, in the end. Okay, so this is the two condition. Okay, you need. Then the alternating series is okay. So geometrically, how should you think about this number here? So let's say B1 is some positive number. Okay, 0 here. And then what happened? Okay. So let's label this B1 first. Here's B1. Okay, B1. But your B2 is smaller than B1. Okay, but B2 is negative. So what does it mean by negative? You go backward. Okay, so you go backward. So you go backward, B1. So this line here means what? You take B1 plus B2 minus B2. Okay, so this is the second term. And then B3. B3 is small, go to the right, but smaller than B2. Okay, so we have to go right again. Okay, so here is B3. Okay, and then let's label this as S3, the third partial sum. Okay, and then you go back. So how should I draw it? So I use this. So you repeat B4, B5, B6 like this. So okay, let me use pointer, maybe easier. So B4 like this, B5 like this, and sorry. Okay, so you take B4 minus B4 plus B5 minus B6 plus B3 and then B7 and then like this. Okay. So eventually you will hope that your finite sum maybe lie between here. Okay, so this is your infinite sum. Okay. Okay. So in particular, what can you see here? So the infinite sum lie between 0 and your BI. Yeah. Okay. Okay. Another thing you can check here is another thing you can see from this picture should be if you take your infinite sum minus your n partial sum. Okay. This absolute value here will be less than Bn plus 1. Okay. You know what does this mean? So you take this S, okay, minus Sn. Okay, this part here should be less than Bn plus 1. So in this case here, S minus S2 is less than B3. Can see this example here. This is true for all n. Okay. So let's say we take x here. Okay, x in the middle here. We take away x2. Okay, which is this difference, right? Okay, this difference here, no matter it's on the left or on the right, okay, is always less than or equals to Bn plus 1. Okay, can see it from this example. First, understand the statement first, then we will prove it in general. Okay, can you see the example here? So S minus S2, okay, which is the middle difference here. Okay, so here is S minus S2 is less than or equals to B3. Yeah. Can you think of it why it makes sense? Can you think of it? Can you think of it why it makes sense? What is S? Infinite sum, right? Okay. It certainly contains more things than Sn. Okay. Yeah. Yeah. Question? Any question? Okay, so maybe let's try and prove this general case. See why is it true. Use red again, so I'll make it white. Okay. So why is this true? So the first equalities will hold. Okay, if I replace S with Sn plus 1, this will hold. Is this true? Why? Who say yes? Why? The number is getting smaller and smaller, so the difference is smaller and smaller. That is true, but how you express it mathematically? How? AN? Correct. Yeah, okay, so what you say here is this is just equals to modulus of Bn plus 1. Okay? Why? Because this is just by definition of partial sum. Okay, so this tests your understanding on this partial sum already. Okay, so okay, maybe you are not familiar with this sum. How about we write like this? So B1 minus B2 plus B3 plus dot 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 plus until minus 1 to n plus 2 of Bn plus 1. And then this guy is what? This one is 1 B1 minus B2 plus B3 plus dot 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 plus minus 1 to the n plus 1 times Bn. Okay, so you take the difference of these two. What's the difference of these two? It's just the addition Bn plus 1 term. Okay, so you left with a Bn plus 1 here. Okay, so why this first inequality is here true? What is x? X here has more stuff, right? More stuff, meaning what? So you have a B1 minus a B2. You have all these Sn plus 1, right? Okay. So you have a Sn plus 1 plus Bn plus 2. Bn plus 2 plus Bn plus 3 and so on. Okay. Yeah. So why? Any idea? No idea. No idea. No idea. Larry, any idea? Ivan, Ivan. Any idea? No idea. Huh? Want to sleep already? All the terms on the left is smaller or than all the terms on the right. What do you mean? So on the right, there's only one term, right? Only Bn plus 1. On the right, there's only one term. On the left, there's infinitely many terms left over. Correct or not? Correct or not? So on the left, there's infinitely many terms left over. Okay, in particular, what are these terms? What are these terms? These are Bn plus 1. Okay, maybe we don't know the sign yet. So let's put the sign on. And then Bn plus 2, Bn plus 3, and so on. So why this thing? There are infinitely many of them. Still less than Bn plus 1. Yes, correct. So why? Why is this true? Left hand side have infinitely many stuff. Right hand side only have one thing. So why you add up so many things are still less than the one thing? Decreasing and then Okay. Or did I give the wrong equality or not? If I cancel this term from both sides, right, what do I get? I'll get the leftover less than 0. Is this true? Yeah, you don't know. Let's say if it's positive, then it will be false. Right? If it is positive, then it will be false. Can fix it or not? Uh-huh.
Is definitely a different sign than n+1.
You mean like this? Yeah, different sign. Yeah, sure.
Yeah.
And then
They are different sign.
yeah.
So if I add bn+1 and
Mm-hmm.
I take their modulus,
Mm-hmm.
it will definitely be smaller than the modulus of bn+1 itself.
Okay, so let's write down what you say. So, for example, like this. Okay, good. So let's say like this. Right. So they are different by sign. Okay. So what do you say? So we know that bn plus 1 is always greater or equal to bn. Okay. So and then this whole thing is always what? Smaller or equals to bn. Is this true? You said this is true.
So however, in the end, it will be positive, right?
No, okay, right. So let's try a number, right? So let's say like this. So 4 minus 2, is it less than 4? And then 2 minus 4 or 4 less than 4. Okay. Right. Yeah. Okay, this is true. This is true. So can we apply it? Can we apply it or not? So we have another equation. So how about whether this is true? Is this true? So what inequality we have? So if bn plus 1 greater or equal to bn, how many we have? Bn. So we have bn plus 1 greater than bn plus 2 greater than bn plus 3. Like this, right? So here should be bn plus 2. Okay. Yeah. Okay. Yeah, like this. Okay. Correct or not? Add modulus where? Okay, so actually we assume this bi to be greater than 0 already. That's why we put the minus plus sign. Otherwise, the plus minus sign will alter our series again. Okay, so we start with a bi positive. Okay, so our bi is positive. Okay, and then we have this decreasing sequence, and then we take this sum. So you take a ruler, okay, and then you cut it, and then you add it back, but you don't add it back until the first place. You don't get it, huh? Okay. So, okay. Let me take a bn plus 1. Okay, I take a bn plus 1. Okay, I cut it small, bn plus 2. Okay, but the next thing I add is at most bn plus 2. No. The next thing I add is at most bn plus 2. At most. So at most you will get back your bn plus 1. But most probably you will be less than bn plus 1. And then you repeat the process. Okay. So you will never get bigger than your original length. Make sense or not? Okay. So this is due to the inequality we have. Okay. Okay or not? Question. Then I'm going to repeat this part again. Do you get it? Can I understand or not? So you see on the left hand side, you start with a bn plus 1. Okay. And then you remove something smaller at bn plus 1. Okay, so let's say something like this, bn plus 2. Okay. But bn plus 3 is at most as big as bn plus 2. So you're gonna add at most bn plus 1 back. Can or not? Okay, so another thing you need to remember here is their sign is different. Okay, so let's say like this, plus minus plus. Okay, so you start with a bn plus 1. You remove bn plus 2. And then you add bn plus 3. So how big is bn plus 3? As big as bn plus 2. So at most you can go back to bn plus 1. Okay. And then you repeat this process here. So at most you can go is the first term you have. Yeah. Okay. At most you can go is the first term you have. Most probably you will go smaller and smaller, or fix at some places. Okay. Can get it? Hello. Okay. Please, if you have questions, just ask. Okay. I mean, if you just start anywhere, you just ask. Okay. Start anywhere, just ask. Because if you start, then you won't understand what I say. Okay. Question? No. Okay. So remember the process. Forward, backward, forward, backward. Okay. And then how much you should go backward, how much you should go forward, controlled by your the term, inequality of the term. Okay. Why are we going forward and backward? Because we care about alternating sign. Okay, alternating series. Okay. Yeah. Okay. So let's do examples. So we have harmonic series diverge, but we have alternating harmonic series converge. Series converge. Okay. So what's a alternating harmonic series? So you just put minus sign alternatingly. Alternate minus sign. Okay. So to use alternating series test, we need to check two conditions. Okay. One condition is your term must be decreasing. Okay, your term must be decreasing. Second condition is it has to decrease as fast. Okay, need to go to 0 until you get 0. Okay. So for the first condition, is it true? So is it true that 1 over n greater or equal to 1 over n plus 1? Yes, right. Why is it true? Because n plus 1 is always greater or equal to n. Okay. Why n plus 1 is greater or equal to n? Because 1 greater or equal to 0. Okay. So you can see this thing actually important. Okay. Sometimes you will see axiom says that 1 not equal to 0. Okay, to prevent some stupid thing happening. Okay, how about 2? Okay, I think 2 is relatively easy to verify, right? This is just the limit of 1 over n, okay, which equal to 0. Okay, so altogether by the alternating sign series theorem, okay, the alternating series theorem, the alternating harmonic series converge. Series converges. So, how about I let you do one exercise so that you don't fall asleep. So try this example here. 1 over n factorial. Okay, alternating sum of 1 over n factorial. See whether this converge or not. Conversion. Try first. Check whether it satisfies the two properties. Alternating sum of 1 over n factorial. Quite easy one, this one. Converge or diverge? Conversion. So first inequality, what you have to write down? Bn greater or equals to Bn plus 1. Okay, so Bn is 1 over n factorial, and then Bn plus 1 is n plus 1 factorial. So this is equivalent to m plus 1 factorial greater than n factorial. Okay. So this amount to what? This just amount to m plus 1 greater than 1, which is n greater than 0. Do we want strictly greater or greater equal? Greater equal. Okay, greater equal. Is our n greater equal to 0? Yeah, our n start at 1. Our n start at 1. Since it's always greater equal to 1. Okay, good. Very good. So 2, how about 2? Limit of 1 over n factorial. So this one is obviously 0. Okay. So altogether by ST, so the alternating series of 1 over n factorial converges. Okay, converges. Okay. So far, okay. Hey, by the way, do you guys see the previous year notes? The empty one on Moodle. Do you guys see that? You can use that if you want. Yeah, I think, huh? Yeah. I mean, if you don't want to copy everything, there's question already there. so you can use it. Yeah. And what I want to say, yeah. Yeah, mostly I'm following that. And then you can read before. Did you read before you come? No, right? That's why you feel sleepy, because you don't know what I'm talking about. Let me tell you, I got another class, AIT. They read before they come. Yeah. They read before they come. And then they listen better than the other MAT class. MAT class also like you. Sleep. Confused. Not your class, but I mean the other class. But it's similar to you. No, no. Your senior. Yeah. Okay. No, I mean pass already. Last semester. So my suggestion is, if you were confused, you will feel sleepy, please read first before you come. Okay. Yeah. Read first before you come. Okay. Okay. Next. Let's try one more and then we will go to the next part. Let's try this one. Okay, let's try this one. So the alternating series of n squared over n cubed plus 1. Does this converge or not? Does this converge? Does the series converge? Does this converge? Does this converge? One property is easy to check, but the other one you need to try. Which one is easy to check? Limit, yes. Limit go to 0. Okay. How about the other one? How to check decreasing or non-increasing? Yeah, non-increasing. You know why? You know why they keep the non-increasing property? Why they allow equal sign? Series converge or diverge? Constant ordinary series converge or diverge? And partial sum converge or diverge? Diverge, right? Because it alternates between two numbers. Okay. So why you still allow equal? Why you still allow? There's another property, right? There's another property that help you to reduce Bn. Maybe you have some equal terms in the middle, but in the end, you have to go to 0. Bn have to go to 0. That's why you have two property to check, and not just one. Okay or not? Okay. Yeah. So I'm trying to play around with this theorem. Okay. So if I reduce a little bit, can or not? Then if I reduce more, does it still work? Then you need to ask yourself this question. Okay. Because I believe if you can come to max degree, I think most of you can do calculation already. Okay. So now you need to go one step further. Why this calculation work? If I change a little bit, does it still work? Or some problem will pop up. Okay. Can we solve that problem or not? With the other way. If you can solve the problem with the other way, then you produce a new theorem. Because no one knows. Correct or not? Okay. Yeah. Okay, so you need to discover, play around with the theorem. Okay. Yeah. Okay, so come back. So how to show decreasing? How to show decreasing? Oh, you want to start with Bn greater than or equal to Bn plus 1, is it? Right. Okay. So so you will have this big problem here. Have you try and expand things out already? Yes. So you use the binomial thing. I also guess not good. Anyone try this method or not? Does anyone try this method? Try and expand everything out. Anyone try? No. You can try, but maybe you shouldn't try. Okay, but so what to do here? So remember last time we talked about the decreasing sequence and increasing sequence, right? There's one way we can check decreasing, increasing as well, which is computing the gradient. We can check the gradient as well. Okay. So when is the function decreasing? The gradient is smaller than 0. Okay. So if this is discrete, right? Okay, we can just join line to look at the real function. So if the real function decreasing, this discrete thing is also decreasing. Okay, so let's compute the function. So let's look at the function fx equals to x squared over x cubed plus 1. Still remember or not? Last time we have discrete sequence. But we can look at the function that define the that give the sequence, correct? Okay, and then if this function is decreasing, surely the discrete number also decreasing. Make sense or not? Okay, so now we need to check whether when is this function decreasing. Okay, so I quickly compute this gradient. Maybe you can check whether it's correct or not using the quotient rule. Yeah, I quickly compute it from last time. We get this as q plus 1 over 1 squared. Okay, so we want to make sure this thing is less than 0. So when does it less than 0? When is it less than 0? The denominator is positive or negative? Always positive. So you need to make sure your numerator less than 0. So how to make sure your numerator less than 0? Either s less than 0 or minus 2s cubed less than 0. They cannot both two negative. Correct? Okay. If x is negative, what happened to s cubed? Also negative. So negative plus negative is positive. So still okay. Okay, but our n is positive, right? Okay, we don't care about s negative part because we care about n which is positive. Okay, so how so if x is always positive, okay, so how to create a negative term? So s is always positive. So our n is positive integer. Okay. So how? So this part is already always positive. We need to make sure. So this part is positive, this part is positive. So seeing what happened, how to make the whole term negative. There are 3 terms here, right? So I already know that my S has to be positive. My denominator is also positive because it's a square. How do I make the whole term negative? Can you understand my question? Okay, yeah. So how to make the whole term negative? Huh? Yeah? Yeah, just say up. Sorry? Louder. How? Huh? But can you understand my question or not? Yes, can. So do you know how to make the whole term negative or not? No. A bit dangerous like this. A bit dangerous, eh? Okay, so Ivan, how to make everything negative? So we want to make sure minus x cubed is less than 0. Okay? Yeah, so in this case here, what do we get? We get s is greater than cube root of 2. So what's cube root of 2? Greater than 0. Not enough. Rough. What is cube root of 2? Square root 2 is 1.4 something. So cube root of 2, cube root 2. Or still 1 point something, is it? Sure. Like cube root 2. 1 point what? 1 point what? 1 point. 1 point what? Calculator. 1.2599. Okay, 2.99. So you see, the s have to be greater than 1.2599. So meaning this only works when n equals to 2 and onward. Okay, so the first term is not decreasing. Okay, so what? So what can we conclude here? So by the alternating series test, we can only conclude that when n start from 2 to infinity of the alternating series, it converges. Okay, but my series start with 1. So how? Just add back the term. In other words, what? Finite terms doesn't affect the convergence. Okay, finite terms doesn't affect convergence. Okay. So since finite terms, addition of finite terms affect the convergence. So the original series converges. Okay. What happened is you just take the convergence sums and then add back your finite terms is your new sum. Okay. Any question? No one. So there's a problem of finding the sum up to decimal places. Okay. We don't do this example in class. You can try. It's in the past lecture notes. I won't focus on that thing. Okay. Should we finish now? Or maybe take a break? Or take a break first? Okay. Okay, let's take a break until 5:19.
它是那个它是这样子下来，是吧？
啊，OK 呀。
I mean 讲它的这样它的那个 slot 会觉得点，
要。
如果要导回这个点啊，这样会用到这个吗？还是在另一个
OK，
I mean
我的逻辑是这样，就是你有这个 sequence，你可以 consider 它的 real function 嘛，对不对？但是这个 real function 如果是 less than 0的话，它 gradient 这样代表它是不是 decreasing？
就是
所以它 decreasing 的话，是不是代表你选的来，因为你拿的是 n 跟 n 加一，OK，所以它一定是 decreasing 的。
就是
所以你刚才问的问题哦，
我的问题就是我会通过我知道就是I mean 我的 slot 会小于0，然后就可以找到
你就可以 show 到 fn 加一是 less than equal to fn，你想这样哈？可以，知道为什么可以吗？
我要讲描述我那个问题
你再描述看。
它是个点，它是一个点，它不是一个曲线哦，它是每一个都是一个点。
对，没有错。
我讲
点是不是从那个曲线来？我想问你，
从曲线不是点组成曲线，
点是组成曲线，但是现在 let's say 你从一个曲线，你 start with 一个 curve，
我 start 我一个 curve，
对，你 start
然后
with 一个
然后我这个 curve 这样说下来，然后就这个点的 slope，我要找的是这个点，I mean 要讲。
OK，可以，就照你那个讲，你继续讲，然后呢？你对了，你继续讲，
I mean 我就可以一直这样走下去。
然后呢？什么问题呢？
我
问题在哪里？
想描述
我可能知道你要问什么，有一点蛮深奥的这个东西。
我知道，我觉得不是
OK，
像 basic
你要得到什么东西？现在先问你要
我得到
什么？
我得到这个 x，对吧？得到这个，像我
什么 s？
那个
没有人要得到这个 s 啊，我们要得到是这个东西，这是我们要。
我知道，因为 x 它是大于1点多嘛，
啊
对吧？
，OK，
等于1点多，
啊，
所以
然后
至少我的 n 要大于这个大于1.2，然后它是一个整数。
，OK，好呀，
我就
没有错，
等于
没有错，and then，呀，没有错，然后呢？对啊，没
我要
有错的，
描述那个问题的时候，我就一直跟他卡住。
对啊，没有错了，然后你要得到是这个东西。
为什么我可以通过计算这个，我找回这个的答案呢？
哦，这个的意思是说，这个是说，我们找这个是说什么 x 的时候，它的 gradient 是小于0，然后它这个告诉你，所有的 s 在1.2这个东西，就是 cube root of 2之后，全部都是在下降，
Yes，
就这样，
哦，
对吗？我 set 的这个问题是说，什么时候这个 s 它的 f prime 是小于0，然后我算出来是当 x 大过，每当 x 大过 cube root of 2的时候，可能这个叫做 cube root of 2， 它一定是下来，它一定 decreasing。
哦，所以它就是在这个区间
点过后它就开始下。之前呢？之前它不下哦，它之前可能是再上去哦。
哦。
OK。
一样。
这学期要拿什么课？哦，上次你跟我讲的吗？你们这学期拿什么课？
我吗？
啊，
Regression analysis，
什么 analysis？
regression
OK
analysis，
OK OK。
然后 advanced linear algebra，
哦，哎呀呀，
然后还有一个 C and C plus，C plus，
他们说那个很难抢。
对，
OK OK。
这是第2个学期考，
所以你是3个吧？
还有一个 computer skills for beginners，
哦 OK，
那个是记忆课，
可以。
然后就没了，
对，
修了20
那你是第几个学期？第几年？第几个学期？
第3年第1个学期
第3年第1个学期啊，所以还有1个学期就毕业了。
啊，结束了。
可以。所以你的 FYP 是谁？
我不知道那个名字怎么念，
不知道老师。
我知道是哪个老师，但是我不知道那个名字怎么念。
哦，哪有人呢？
华人，
马来西亚还是中国？高清用？
可能吧。
男的。
KOH，
哦 KOH 女生啊。新来的老师。OK。
然后他是不教数学专业的，
谁呀？
就是我的导师说是不教数学专业。
他教还没开始教吧？他刚来吧？他还没开始教，还没教到，他刚来吧？他上学期才来的。好像还没教到。
独立那个叫什么？
谁？
独立
哦，独立什么课？
不知道，
哦，可能是 calculus 那样子。
一直在教 calculus 吧？
好像是。
我们那一届就是他教的 calculus 吧？
上一届好像有。
2109。
OK。哎，2202好像，哎，2022好像也是。教一个一般，有一教一般2022，后面也是。
你觉得懂不懂？
我看你真的是累积掉，真的是累积，不行了。
但是还是有分的。
是累积的那种。
Okay, let's continue. Done. Done. Okay, let's continue for the last hour. Okay. So what can we say about, for example, you see harmonic series diverge. Okay. But if we make it alternating, it converge. Okay. So we want to describe this phenomenon. Okay, we want to describe this phenomenon. So if the infinite series of an and infinite series of absolute value of an both converge. Okay, if both converge, then we say that sum of an is absolutely convergent. Okay. So the series converge. You take the absolute number of an, add them together, also converge. Then the series is absolutely convergent. Okay. Converges absolutely. Okay. The second condition is the harmonic series. Okay, harmonic series. So we will say that if the sum of an converges, but if you make all the terms positive and add it out again, it diverges, then we say that the original series is conditionally converging. Okay, convergent. So for example, what's the example of a conditionally convergent? Conditionally convergent. What's the sequence that converges, but when you take absolute value, it diverges? Harmonic series. So the harmonic series, not harmonic series, right? It's alternating harmonic series is conditionally convergent. Okay, why? Let's check. 桥通啊，桥通. Okay, so why alternating harmonic series conditionally converge? Definition on here already. The definition is on here. So what's the alternating harmonic series? Sum of alternating 1 over, let's call it I. Okay. How to check something is conditionally convergent? Tell me. Conditionally convergent. How to check? Can see or not? Can see? How to check something is conditionally convergent? Can see? Okay, so how to check something is conditionally convergent? What do you check? Hello. Excuse me. Are you there? So how to check a series is conditionally convergent? Check in what? How to check? check that sum of AN is convergent. Is that all? Anything else you need to check? Huh? Here. You look at wall also don't have here. In front here. Absolute value. Okay. So this is an absolute value. Okay. Take absolute value of AN. And then what? Divergence. You need to take the sum of absolute values. Okay, you need to take the sum. Okay, the sum diverges. Okay, so in particular, this alternating harmonic series satisfy this condition here. Okay, because alternating harmonic series converges by what? By what theorem? Yeah. Why alternating harmonic series converges? By what? Like what's the reason? We just show it 1 hour ago. Yeah, so why alternating harmonic series converge? Yeah, that one is one thing you need to check. Yeah. Okay, these are two conditions you need to check. So what's this test? What's the name of the test? What's the name? Alternate series test. Okay. Yeah. So it converges by alternating series test. Yeah. So AHS converges by alternating series test. But okay, like what Chao Tong said just now, if you take the absolute value of AN, okay, you sum them together, what do you get? But harmonic series diverges. Okay, last time we used the Gauss proof. Okay. I think very good. So you see, seems like when I observe, right, Hanwei is more towards like learning the method, okay, more than the name. Okay. So this is the one thing you need to learn is what is alternating series test. Okay, what's the thing you need to check? Okay, after you know how to do it, you need to remember the name. Why name is important? Why name is important? When I see you, right, I cannot say, oi, 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 that guy come here. Right, you have to call the name. So sometimes name is important for you to communicate. Okay, yeah, maybe it's not important for you to do calculation. I just check these two, and then there's a theorem tell me that it converges. But the name is very important to tell people that, hey, use this. Okay, and then everyone will use the same language. Okay, we know about this name. This name talk about this thing. Okay, so name is very important. Okay. Okay. Next. So we'll go to absolute convergence test. Okay, so absolute convergence test says what? So if the absolute value of AN, okay, and then you take the sum, it converges. Then the original sum also converge. Can you roughly see why this is true? Can you roughly see why this is true? The left-hand side one is always positive. The right-hand side may be sometimes positive, sometimes negative. Okay. So you see, always positive one already converge. And then if you take negative, then surely the number is less. So it converge. Can or not? So you need to develop some intuitive idea first. Okay. Okay or not? Seng, what's the idea of this proof? What's the idea of this proof? Huh? Why you guess this statement here? You want to try? You don't want to try? Okay, try. Okay, please try. Okay, Larry, help her. So why? No. Tell us. Mhm. And then
The sum of strictly positive terms, assuming that they only differ by the sign, the sum of all positive terms will be greater than the sum of just the terms that may be positive or negative.
okay, good. Okay, so if the very big, if all the positive term add up is finite, then if you take some of them to be negative, it will surely decrease the finite sum, but it's still finite. Okay. Okay, so how to prove this? So we quickly, this proof is very short, so we just quickly show it. So so what we want to show, okay? So very important in proving, you need to write your goal first. Okay, your goal is very important. So your goal is to show that sum of an converges. Okay, so we're gonna play a trick here. We are going to use the direct comparison test again. Okay, let's do a trick. So 0 is less than or equals to an plus absolute value of an less than 2 times absolute value of an. Okay, does it make sense? An may be negative, but absolute an must be positive. So if one of them negative, one of them positive, then they cancel out. Or if both of them positive, they add up. Okay, but once they add up, it is no bigger than 2 times absolute value of an. Okay, and always greater or equal to 0. Okay, so we're going to play this trick. So what is our condition given? So suppose the sum of absolute value of an converges. So are you happy now? Should you be happy? Happy or not? Why not happy? You see, sum of absolute an converges. Okay, you have some inequalities here. Okay, but not quite there yet, but it's almost. What's the difference between 2 times absolute an and absolute an? See, what's the difference between absolute an and 2 times absolute an? This term and this term. This. What's the difference? Louder. Say, never mind. It's okay. Just say it. Jia, you sure it's Jia? Jia what? Jia. Sorry, if I confuse you a lot. So what's the difference between these two? My question is, what's the difference between these two? 两个。Okay. You really see things differently, you. Yeah, you can think of them as add twice, but a more convenient way to think of it is 2 times 2 times this number, can or not? 2乘 ，OK？ 你可以想成是2加2次 ，but 可以加 ，you can add, but I mean but to apply the property of series, you still can because we can do the linear thing. Yeah, you can. Okay, but yeah, but make sure you can think of it as a 2 multiply as well. Okay, both. Okay, so let's say we follow what Si Ying say here. So let's follow her thinking. Okay, let's say we write like this. So suppose this absolute value of an converges, then 2 times absolute value of an also converges. Okay, because of what? Because we are taking the sum of 2 convergent series. Okay, you can do this. Okay, because you are taking the sum of 2 convergent series. Okay, if I think of it as a multiplication, because I just multiply a constant to a convergent series. Okay, both can. But you need to be aware if I put a 1.5 here, you cannot think of it already. Think of it as an addition. Okay. Okay, good. So this one converge. So the outside one converge, meaning the inside one also converge. Okay, so by direct comparison test. Sum of an plus absolute an converges. Okay, good. So what's our goal? Still remember our goal? Sum of an converges. Okay, so there's an extra bit here. How to get rid of this guy? Okay, so how to get rid of this guy here? So what is this sum? Let's try and write it up. So this is A1 plus absolute A1 plus A2 plus absolute A2 and so on, like this. Okay, so how to extract the sum of an out of this? What can we do? Switch the position. So meaning we can rearrange. Okay, we can rearrange. Okay, we can rearrange. We can rearrange like this. Of course, to be very pedantic, if you rearrange, you need to use associativity and then commutativity. Okay, you know what am I saying? Associate. So A plus B plus C equals to A plus B and then plus C. And then A plus B equals to B plus A. So this one is associative. Then the second one is commutative. Did you learn this in your discrete math or not? That's right. Okay. So you should use associativity and distributivity. Again, to rearrange. Okay, so this one is what we call rearrangement. Okay. And this implies that this is just split up as a sum of an plus sum of absolute an. Okay. So what do we know? We know the whole sum converges. Okay. We know the absolute an converges. Surely the sum of n should also converge. Okay, because you have a finite number equals to some number plus a finite number. So finite number minus a finite number, you still get a finite number. So sum of an converges. Okay, but be aware, be aware. So this rearrangement of infinite series, right, doesn't always work. Okay, later I will talk about it. It only works when this series is convergent. Okay, only when convergent. If not converged, you cannot simply rearrange. Later we'll see example, or I'll tell you some example. Okay. So okay, I think I mispressed something. Okay. So let's try and use this first, and then we will talk about rearrangement later. So let's try and apply this test. Okay. So when can you think? When do you think you can use this test? Let me go back to the statement first. Where's the statement? Yeah. So when do you think you can use this test? From the theorem, you should think about possible situation already. What? Sorry? Yeah, so maybe you start with an alternating series, okay, and then you check the absolute value of your alternate sequence, okay, and then you check the series. If it converges, then the alternating series converge. Maybe later. Okay. So let's see one example. So this is an example of alternating series. Okay. We want to show that this converges. Okay, we want to show this converges. So if we're gonna use absolute convergence theorem, what should we do? What should we do? Add modulus. Okay, so we add modulus to the series. Okay, we add modulus to the series. So let's consider this series here. Okay, this series is what? It's just 1 over n squared. Why does this converge or not? Why? P series. Okay, so this converges because this is a P series. P series when P equals to 2, which is greater than 1. Okay, so by the absolute convergence test, the series, the alternating series converges. Okay, so it converges conditionally or absolutely? Conditionally or absolutely? Why? What's the definition of absolute convergence? If series n, if the series and the absolute value version of the series both converge, then it absolutely converge. Okay, so absolutely means no matter what you do, you converge. Okay, what you do is you take absolute value, so it absolutely convergent. Okay. Okay. So what's the other way you can check? What's the other way you can check this alternating series? What's the other test you can use? What's the other test you can use? Alternating series test. Okay, so you check Bn is greater than Bn plus 1. Okay, I think this is true, right? Bn greater than Bn plus 1. Okay, Bn is greater than Bn plus 1. Because what? Because n plus 1 squared is greater than n squared. Is it true? 1 over n squared is greater or equal to 1 over n plus 1 squared. Okay, this is amount to 1. So let's say we want to use AST, okay? So this is amount to n plus 1 squared greater or equal to n squared, which is 2n plus 1 greater or equal to 0, which is n greater or equals to negative half. Yeah, everything. Okay. Yeah. So this is decreasing. Limit go to 0. Correct, right? So this is the first condition. The second condition is limit of 1 over n squared is just 0. Okay, so you can also use AST to prove this. Okay, so so which one to use? Depend which one is faster. Okay, because you will be doing this in the exam condition, so you need to finish on time. So how to decide which one to use? You need to do more exercise. Okay, try more exercise. Try more exercise. Then you will see faster to decide which one to do first. Okay. Okay, so the other exercise I'll leave left as homework. If not, I will do it at the start of the next lecture, but I haven't finished yet. Let me finish let me go a bit further, then we'll finish. Okay, so so should we talk about the rearrangement stuff? Okay, maybe I just mentioned about it because I think we barely test this in exam. So I'll mention about it. It is in the lecture. Okay. So what do I mean by rearrangement? So rearrangement of a series is just rearranging the order of the terms. Okay, just like just now, we can move terms forward and then backward. Okay. So when can we rearrange the series? So when the series is absolutely convergent. Okay, absolute convergent means what? The sum of the series converges, and then the absolute value of the series also converge. Okay, with a sum x. Then, okay, then you can arrange it anyhow you like to have the same sum. Okay, so this makes sense, right? This is what we use in the proof. So if it converges, okay, absolutely, then you can rearrange it to get the same sum. So how about the next one? So if AN is conditionally convergent, okay, conditionally convergence means what? Only sum of AN converge, but if you take the absolute version, it doesn't converge. Okay, and then what? And then you can take any value R. Okay, so this is the special things about conditionally convergent series. Okay, you can rearrange the terms to get any sum you like. To get any sum you like. Let me show you some example. Zero can you can get 0, but let me see. So for example, let me give you an example. Okay, so alternating harmonic series. Okay, 1 minus half plus 1/3 minus 1/4 plus 1/5, and then so on. Okay, so the theorem says, or the rearrangement theorem says what? Says that if you have a AN which is conditionally convergent, and then you pick any real number you like. Okay, any real number you like, your favorite real number. Okay, then this is the special part. Okay, there exists a rearrangement of the same AN, okay, such that the sum is equal to R. Okay, so you can do this. We won't prove this. I'm not sure the textbook have this proof or not. Okay, but for example, okay, let's start with this example here. Okay, so alternating harmonic series here is conditionally convergent, so it satisfies this theorem. Okay, so for example, what? So for example, we can prove that. So it can be shown that this convergence series here converge to log 2. Okay? Converge to log 2. Okay. So if what do I do? If I multiply the whole thing by half, okay, and then I play around with this series, I add some 0 into this series, okay. What do you think I get? So I multiply the series by half, and then I add a bunch of 0. What do you think I get? So I multiply half to this series, okay, and then I add a bunch of 0. What do you think I get? I multiply half to the whole series, okay, I add a bunch of 0 alternatingly. So what do I get? Yeah, sure. No, not all positive term. I also get this alternating sum, terms popping up. But what's the sum here? 1/2 of log 2, right? Okay. But let's say if I add these two together, what do I get? I add these two together, what do I get? 1 1 1 plus 1/3, and then plus 1/5. Minus 1/2. And then plus 1/7, minus 1/4, and then so on. Okay. Equals to what? 3/2 log 2. But can you realize that this is a rearrangement from the alternating harmonic series? So I move minus half to the back of 1/3, and then minus 4 to all the way behind 1/7, and so on. Okay. But just now we said that alternating harmonic series is log 2. But now we get 3/2 log 2. Okay. Yeah. So this is the theorem. Kind of weird. Okay. Seems like it's not well defined. But it's a theorem. Okay. Okay. Yeah. Any question? Yeah, we won't prove this theorem, but if you're interested, you can have a look. And maybe you can write it in your project. Okay. Yeah. You can rearrange it to any number. Can we introduce 2 tests before we go home? Okay, let's finish up these tests, and then we will start our series on Thursday. Okay, let's finish up quick. So the next test is the ratio test. Okay. Thankfully we won't prove this. Okay, just use it. So ratio test. So ratio test is good. Okay, you don't need. It's the best for me. Okay, best tool for me. Maybe you can try it. So the thing you see about series, right? The first thing I try is ratio test. Because ratio test, you don't need to compare with anyone else. Okay, you just need to check your own terms. Okay, so what's the terms I take? So here say about ratio, right? So what kind of ratio we take? So the ratio we take is exactly an plus 1 over an. Okay, so how fast the an grow? Okay, so if the growth is less than 1, then the series converges absolutely. Okay, not that we take absolute value on our ratio. Okay, not that we take this absolute value. Okay, and then what? And then what are the cases? What are the other cases? We have cases L less than 1. Surely we also have cases when L is greater than 1. Okay, or infinity. Okay, or infinity, or L equals to infinity. Then the series diverge. Can make sense of it or not? You see, the next term over the previous term, less than 1, what does it mean? The previous term is larger. Okay. And then if the ratio is greater than 1, meaning the next term is larger than the previous term. Okay. So you should expect it to diverge. But there's a cutting line here. Okay, where's the cutting line? Where's the cutting line? L equals to 1. Okay, good. So L equals to 1, what happened? We don't know. Okay, you cannot deduce anything. Okay, you cannot deduce anything. So you need to find other method if the limit is equals to 1. Sometimes it converge, sometimes it diverge. Okay, so if it is equal to 1, it doesn't tell anything. Okay, so for example, let's check that this alternating series converges absolutely. Not that one very good condition here is this ratio test, right? Doesn't tells you series converges, but also converges absolutely. So meaning the infinite series converge, and if you take the absolute value version, still converge. Okay, it's quite strong. Okay, it doesn't just tell you the series converge. Okay, so let's compute the ratio here. So what's the ratio here? An plus 1 over an. Okay, an plus 1 is minus 1 to the n plus 2, 3n plus 1 over n plus 1 factorial over minus 1 to the power n, 3n over n factorial. Okay, so you see, the good thing about this absolute value is what? You can throw away your sign. Okay, you can throw away your sign. All the sign will disappear. So what do you left with? So you just left with 3n plus 1 over 3n, n factorial over n plus 1. Don't be afraid if you see these factorial thing, because they will cancel out, because they just differ by n plus 1. Okay, so what in the end you will get 3 over n plus 1. Okay, 3 over n plus 1 is always positive. Okay, so we can get rid of the modulus, absolute value. We can get rid of the modulus. So this is just equal to limit of n to infinity, which is just 0. Okay, 0 is less than 1. So by ratio test, the series converges absolutely. Okay. Okay. Okay, so next, there's another question we will leave as homework, and then we'll quickly introduce another last test before we go home. So it's called the root test. So the root test is really similar. So I want to introduce together. So similarly, you start with a infinite series. Okay, we won't prove this as well, so don't be worried. So what's the root test about? So there's a root word. So what's a root? What's a root? What does root mean in mathematics? 开根号. Okay. So take square root, cube root, fourth root, fifth root. Okay. Yeah. Okay. So what kind of root we're gonna take? We take n root. N root. N root on. N root of absolute value of an. If this limit equals to L, okay, so how you should imagine this? You should imagine a sequence of cube root, square root, cube root, fourth root, fifth root, sixth root. You see this sequence. Okay, this sequence, if it is converging to L, which is less than 1, same result. The series converges absolutely. Okay, same thing. This is really similar to ratio test. Just the limit terms you take is different. Okay, if it is equal to L, which is greater than 1 or infinity, then the series diverge. Okay, same. Okay, similar. Okay, and then if it is equals to 1, okay, if it is equals to 1, then the test is inconclusive. Okay. Can you imagine how this test is useful? Can you imagine how this test is useful? Taking n root, is it troublesome or not? Is it troublesome taking n root? Is it troublesome to take n root? What kind of situation you think you will use it? I'll give you a more troublesome series. So how about this series here? To the power n. What's this series? So the power is increasing. Okay, so how on earth you're gonna check this? You have to use a comparison test, direct comparison test, limit comparison test, absolute convergence test, alternating series test. Which test to use? Okay, yeah. See, the power here is increasing. Okay? But there's a root test coming to help you. You also can take root when n get large. Okay, so when n get large, you will make this n disappear. Okay. Okay, let me show you. So take limit of n infinity of square root n of the absolute value. Remember, there's an absolute value here. So can the n root go into absolute value or not? And can you go into the absolute value? Can you take n root of a power? Okay, absolute value of a power of n. Can you straight away do that? Yes, man. So I mean, can you like this s to the n equal x? Is this true? Yes. Maybe this is yes. How about this one? Yeah, this is not true. Unsure. But I still want to cancel it or how? You want to cancel it? So n is bigger than 0. Okay, so n is bigger than 0. Everything here is bigger than 0. Okay, so in particular, these are just positive terms. So I can get rid of my absolute. Okay. So in the end, this just reduce to taking the limit of 2n plus 3 over 3n plus 2. Okay. So in which case we will get 2 over 3 because we divide top and bottom by 1. Okay, which is less than 1. So when it is less than 1, then the series will be converges absolutely. Yeah. Okay. Okay. So please go back and do exercise maybe next week. Not next week. Thursday. Thursday, maybe we will do some more exercise and then we go to our series. Okay. We'll see you on Thursday.